you through a thought process, okay? About how all this stuff is related. So, hang on. Yes, next 6 weeks. All right. So let's take a look. We'll look at the variables. Wavelength is equal to frequency, and it's related to velocity. So it's related to both of those things. Now we're going to talk about how the big ideas kind of surrounding how to get there. So if I'm going from wavelengths to frequency, I need to understand what's happening with velocity. And like we were just talked about, when you're dealing with velocity, all right, we know that if you're in the same medium, all right, the big idea is that the same medium, you have the same velocity. Okay, that's the first big thing. Doesn't matter what, if it's a string to string, all right, two things happening in the same string, they're going to have the same velocity because it's the same medium. Okay, the second thing that we could use to deal with velocity is, I know it's tiny, all right, I'll kind of erase that real quick. Whoops. Oh, whoops, not that. People are having trouble reading this. Our equation for the velocity in a medium is force of tension divided by the mass per unit length. Okay? So those two facts are things that we can use to get velocity. Okay? So if we have to end up with wavelengths, we can use that there. Now, if we need to get to velocity, well, there's a couple of facts about frequency. What do we know about frequency when it switches mediums? Huh?
Different velocity.
Different velocity, but what happens to frequency when you switch mediums? Nothing. Nothing happens to velocity when you switch mediums, okay? Like remember we were doing the snaking and I'm sitting up here, right? The frequency comes from how much the source is. In this case, it would be my arm. Or if it was an automated one, it would be an oscillator making it move up and down. That's what causes your frequency. So I could be doing this right here, or I could be doing it underwater. As long as my hand is moving at this frequency, that frequency is going to be the same thing. This also works in terms of, say, sound, okay? You pluck a string on a guitar. The guitar has its own velocity, right? Because it's a medium. And now you have a frequency of that vibration. That vibration pushes against the air. Okay? Now all of a sudden the air is getting pushed. But what frequency is it getting pushed at? The same frequency as the string. Because that's where the origination was that vibration. So frequency stays the same as we move mediums. Okay? All right. So to kind of put that together, we're going to use, to go from wavelength to velocity, we are going to use our knowledge of frequency. The big idea one is that the frequency is the same over different mediums. Okay? And now that's not frequency. We're still talking about wavelength, right?
What's the medium?
What's medium? What it's moving through. Sound goes through where? A wave frequency can go through a string. Yeah. Yeah, it's just what the wave moves through. If you try and talk in water, that's a medium.
So the frequency doesn't depend on like how tight the string is or how loose it is. It depends on what you're moving it as.
Yeah. The how tight or how loose your string is, that's the tension force which comes into being. That affects your velocity.
The tension affects the velocity.
Right, the tension of your string is going to affect your velocity. Okay, right there. Now, I wrote this equation down. This equation, as we're supposed to be talking about frequency, so why did I write this equation down? It's because we can take that wavelength, and the way we're going to use it is that the length is equal to N over 2 is equal to V over F. I kind of rewrote that. So those are the two things that we know about frequency. Frequency is the same over different mediums, and that if I know the length of the string, and remember what that N stands for?
Number of
harmonics. Harmonics. Remember, there's always one more node than harmonic. Okay. All right. So that N stands for whatever harmonic that you're on. Okay. And most of the time, you're going to probably be dealing with first harmonics. Okay. So we know our frequency, we know our velocity, we know our wavelength. The only other variable that we've introduced here is that L, right? So what is L? L is how the length relates to the wavelength. Okay, and that is that the length of the string is equal to the number of harmonics divided by 2 times your wavelength. Okay. And as an aside, if I were to rearrange that, okay, wavelength then is 2L over the harmonic.
The knowledge of frequency, is that part of the velocity?
Yeah, so if we want to go from we have wavelength, we want to go to velocity. All right, that means we need something about frequency. So we're going to need to use our knowledge of frequency to get there.
Oh,
All right, and we can use those two concepts. Okay. And the relationship of length to the wavelength is also got to be a way to kind of manipulate through variables. Yes. We talked about that yesterday. It's due Friday. Yeah. Today. This is the last bit. We're doing a review tomorrow.
Like a review for
over it's different.
What was the question?
review for the test or review on the notes?
Review for the test.
Yeah.
All right, so how many scenarios are in this problem? There's 2 scenarios, right? So if there's 2 scenarios, we know we're going to have to find some kind of commonality between them. In this case, anybody have any ideas on what that commonality is going to be?
Frequency, length.
How about frequency or?
Frequency or length.
Well, the lengths are going to be different because we're finding a separate one. And they have 2 different frequencies, so it can't be, unfortunately, either one of those options.
No word flex. Isn't that everything we talked about?
Huh? No. What is the commonality?
The guitar.
All right, not just the guitar, but the guitar strings are the commonality. And that's important because the guitar strings are the medium. So that means that the velocity that you can get from the first one, yeah, I can't draw. Okay, all right. Our velocity from the first one we can use in the second scenario because both of those velocities are going to be the same. So let's take a look. So this is saying that, so we'll say from here to here, if that's the first harmonic, or the fundamental frequency. First harmonic, fundamental are the same thing. Fundamental frequency. All right, and this right here is 64 centimeters.
Is that supposed to be the guitar string or the frequency?
Oh, that's the wave, the harmonic.
Of the sound it emits?
Right, that's the wave. Thank you for clarifying that. So if that's the first fundamental here, it's saying, well, I'm going to go ahead and I'm going to put for the F key, I'm going to do it right here. And how far do I have to place it from the top of that guitar to end up with a sound, to get that F? Again, and if it's going to be an F, it's going to be a fundamental frequency, right? That's the note. So I can find the velocity through this guy because I have how far it is away and I have the frequency. If I find that velocity, I can use it in the second one to find how far away I'm going to put it. Okay, so we're looking for velocity, so we're going to be doing, whoa, wrong buttons. So velocity is equal to frequency times wavelengths. Okay? Now, we don't know the wavelength, do we? We know the length. And wavelength is equal to, whoops, L is equal to n over 2 wavelengths. All right? And what's the n in this case?
Number of harmonics.
All right, which number is it going to be? All right, so that means our wavelength then is 2L over 1. That's our wavelength. So that means the velocity here is going to be frequency times 2L. There's a frequency of 329 hertz times 2 times our length. I'm going to convert this to meters, 0.64 meters. I do that. We end up with the number of, it is 421 meters per second. Okay, there's our part 1.
421.
Yep. So part 1. Now part 2 is going to be working kind of the same idea, except we're looking for a different value. We're looking for L, the length that it needs to be away from the top of the neck. And length, remember, is related to wavelength. So let's do this. So we know that velocity is equal to frequency times wavelength. We have the velocity, we just solved for it. It's the same medium, so it works. We have the frequency. And we don't want wavelength, we want L. And I know that wavelength, though, is equal to 2L over N. And our N in this case is 1, because again, it's a first harmonic. Okay? So that means velocity is equal to frequency times 2L. Solve for L. Velocity is equal to frequency over 2. So 421 divided by 349 times 2. And we end up with 0.60 meters or 60 centimeters. That means that as we switch from part 1 to part 2, we're going to use the big idea that the frequency is the same in different mediums. Okay? So that's our big idea. The other big... Yeah, Brian. I'll stop. Frequency is the same in different mediums. Okay. Now the first one is to find the frequencies of the fundamental second and third harmonics of a steel wire 1 meter long. So that means that we're dealing with V is equal to frequency times wavelength. Okay. Let's look at the wavelength issue. So wavelength 1, wavelength 2, wavelength 3. That's kind of want to label them. Where L is equal to N over 2 times wavelength. I gotta remember the other one. I don't have the other one as well memorized as this one. I'm just rewriting it smaller. L is equal to N over 2 times wavelength, which is the same thing as saying, if I wanted to substitute that in, 2L over N times, oops, there we go, is equal to wavelength. So that means V is equal to frequency times 2L over N. I don't have my velocity yet, do I?
No.
All right, do I have the information to get my velocity?
No.
Yes.
Yes.
Yes. Because I have the tension, and here's my clue. I have a tension, and it says mass per unit length. Okay? So velocity itself is going to be equal to square root of the force of tension divided by mass per unit length. So it's the square root of 80 divided by 0.002, and that is 200 meters per second. Okay. So I want to find frequency. Okay. I want to find frequency there, so I'm just going to rearrange the equation really quick. The ends are going to be first, second, and third for the harmonics. Okay? And then we just solve for the different frequencies. So let's do that. So frequency then is not that. Let's use a regular pin. So frequency is going to be equal to the velocity times the harmonic divided by double the length that I'm working on. So that means, why did I invert? Because frequency stayed here. I have to move this portion over, the 2L over N. Yeah. I can't just swap places,
I know
unfortunately.
that, but I was thinking the way I thought it was just to move the F and then move the B. That's what
But if you move the F, it would be on the bottom.
Yeah. You can't subtract it.
Yeah, it would be on the bottom. I have to do the inverse,
Oh,
actually.
no,
Right, I'm multiplying. Okay, so that means here we go. Frequency 1 then is going to be equal to 200 times the first harmonic divided by 2 times my length of 1. That gives us 100 hertz. Frequency 2 is 200 times my second harmonic divided by 2 times the length of my wire. So that becomes 200 hertz. Any guess what the next one's going to be?
200.
All right, because again, don't forget, your harmonics are all multiples of each other. So to be honest, we could have said F1 and then go, hey, I want my second harmonic. Second harmonic is 2 times my first harmonic. Third harmonic is 3 times my first harmonic. Okay? This works too. So 200 times 3 divided by 2 times 1 is 300 hertz.
How many frequencies do you have?
We had to find 3 of them. The ones that align with the first, second, and third harmonics. Now we're going to take those frequencies and they want to find out what are the wavelengths of those frequencies in sound. Okay? So, then for the part 2, come on. So for part 2, we need, same idea, is velocity is equal to frequency times wavelength. We have our velocity this time. We don't have to do any fancy math for it. We are going to go ahead and do the same thing where we swap in 2L over N again. Okay, because we're dealing with the length. We're not really dealing with the wavelengths, we're dealing with the lengths of the string. So, we want to, and that's what we're looking for.
We're just looking for wavelength, no?
Oh, yeah, I'm sorry, I'm a dork.
We're just plugging stuff in.
Yeah, I'm a dork. All right, so we're just going to do that. Yeah, exactly what we just said. Velocity over frequency, the first frequency is going to equal our wavelength. So it's 343 divided by 100 is going to give us 3.43 meters. So the first harmonic wavelength in air is 3.43 meters. The second harmonic wavelength in air is 343 divided by 200, which is 1.72 meters. And if you're wondering what that was, it's supposed to be a meter. And for a third harmonic, the wavelength in air is 343 divided by 300, which is what's the last one? 1.14 meters. Okay. So again, these are 2 problems that utilize our knowledge of how velocity and frequency kind of get manipulated within sound, like sound in a string. So that's, yes.
Okay, so I know the velocity on the purple one is the velocity of the sound, right?
Of the sound wave, yeah.
Sound wave. What's the velocity in the red?
The velocity in the
I
red,
have solved for it.
right, is the velocity in the steel wire.
Okay.
Right.
In the wire, not
Yeah.
in the sound wave. Okay.
Right, not in the sound wave. So like if you go ahead and you make it vibrate at the first fundamental frequency, because it's in that steel wire, it's going to have that velocity. So the wavelength will change based on the length of the string. Right? But if you notice that this frequency, it has to have that constant velocity just because it's the medium is what it is. All right. Okay. So we're going to go kind of fast. We have a little bit to get through for the next bit. All right. I'm going to take this off. We're going to talk about actually 4. We'll include the reason why we're talking about with instruments is because it's easier to think of in terms of sound. So we've been talking about strings, right? Yeah, just general part for this part. The strings are standing waves on the highly stretched string. So everything that we dealt with on here, that was with basically like stringed instruments, how that works. Percussion is a standing wave that is produced by the vibration of solid objects when you hit something. We're not going to talk too much about that one. The third one, wind, it also includes brass. Standing wave that is set up in a column of air that is either open or closed. So kind of like recorders or clarinets, anything along those lines. So let's say if you're looking for a standing wave in an open instrument, it kind of looks like this. That's open. This is closed. Remember, because it's closed, you have that node there on the end, right, where it kind of originates out of. Okay. That's really all, so now we're going to go through the details about open and closed. Yeah. The ones that you guys didn't know how to do yet?
Yeah, I tried and I got it.
Well, now we're good. Okay, so open pipes have an antinode on both ends. Remember, can you hear anything right here? Think about it. It's where they cancel out, right? So you can't hear anything at the node. For us to hear something, we have to have an antinode. So if you're on the so if you're looking at a pipe, you're going to have the best sound when you have an antinode on either end of that pipe. Now let's look at this. What is the smallest length of pipe we can have to have a sound? Well, we can't do anything smaller than in the shape, right? How much to get 2 antinodes? How long is this? How long is... Yeah, this part right here, whoops, wrong button. This part right here, that's half a wavelength. So the smallest length of a pipe that you can have, right, and hear something is half a wavelength. So that means that this right here, this is your first harmonic, because this is the first place where we hear something. This is your fundamental frequency.
We didn't need the other page before that?
No, this is where it was. We've already done it. Fundamental frequency / first harmonic. Okay? Now, what's happening right here, guys, is they're just taking you through the math that we've been doing. Like, length is equal to 1/2 times the wavelength. 1 is the first harmonic. Rearrange it to solve for wavelengths and put it into your velocity equation. So that's really just the math that you've been doing. And this down here at the bottom is the same thing. Okay? Now the next one's going to be, okay, so we have half a wavelength. What's it going to look like when we add another half wavelength? So if we put another harmonic on there. Okay? Give you about 5 seconds before I change the page. Yeah, grab the camera real quick. Okay. 3, 2, 1, and that goes. All right, so notice that, whoa, too far for me. I'm looking for something here. They got a little bit out of order. Okay. So this right here is your first harmonic. All right, if I were to cut the pipe off like that, that's our first harmonic. So if I were to go ahead and double this, so it's not half a wavelength, but it's 2/2 of a wavelength, or a whole one. All right, this is what it looks like. It looks kind of, here's our wave. Down, up, down. Okay. Note that we have antinodes on both ends, which means, can we hear it? Yeah, there's antinodes on both ends. So this means that we can hear at the first harmonic, and we can hear at the second harmonic, which is also called the first overtone. Okay. So we're going to do it one more time, just to see if we can see something. So far, first harmonic we can hear, second harmonic we can hear. Let's do the third one just to see if we can still hear. So we're going to take the half and we're going to put another half in there. Well, not necessarily. What we're just saying is like we're proving what's going on here. So that's that. We're going to do it one more time. I'm going to use lines this time. So right here, well, not that line. Right here, that's our first harmonic, right? And there's a node here, and there's a node here, so we can hear. Do it again at the next one. If I double that, Here's my second. Note that that means the end of the pipe here is, this is an antinode, and this is an antinode, so we can hear at all these places. And if I put the third one in, move, we have another antinode. So what we're seeing so far is that we're going to hear all of the harmonics. Okay? So this one is relatively similar to the string, a little bit different in where the important parts are, but it's still like half a wavelength is your fundamental frequency. Okay? The next one we're going to look at is closed pipes. Okay? I'm going to hit pause for a second. You guys get... Okay? Well, is this the right one? No, it's not. Here we go. Closed pipes. So remember, we said a closed pipe, if you have this wall on the side of it, you have to have a node. And for us to hear, we have to have an antinode at the end where it's open, right? Antinode on the end means we can hear it. So in this case, if this is what we can hear, that's your fundamental frequency. That first sound that you can hear is the fundamental frequency. How long is the wavelength to get a fundamental frequency when you have a closed pipe? It's not half anymore, is it?
1/4.
It's only 1/4. If it was the full one, it would probably be going way, it would be way over there, somewhere around the chalkboard section. So our first antinode that we get is when the length of the pipe is 1/4 of the wavelength. Okay? And right here, so again, imagine that this is L is equal to N over 4 times lambda. N is 1. Okay? So, all right, if that's 1/4, you can go ahead and solve for lambda. So it's doing the same thing we were doing. We're just rearranging that to solve for a velocity. You're going to interrupt all the way. Back of the room. Okay? So that's the fundamental frequency of our first harmonic. Now we're going to do the same thing we did with the open pipes. We're going to say, okay, what happens when I put the second harmonic in here? So let's think about that. If this is a quarter harmonic and this is a quarter wave, and this is our first harmonic or our fundamental, then the second harmonic is going to be how much of a wave? 1/2. All right, let's see what happens when we do that, all right? I'm not looking for, it's not showing me what I want. Hang on. My slides got messed up. Okay. So half a wave then would be that. Are you going to be able to hear this second harmonic? No, because at the end where the open side is, it's a node, not an antinode. So we cannot hear the second. We hear the first harmonic, we can't hear the second harmonic. All right? So, what was this saying here? In a closed pipe, you have a node at the second harmonic, so we're not going to hear it. Okay? And so what this is telling us is that for closed pipes, we're not going to hear every frequency. Okay? We're only going to hear on the odd ones. Because if I go ahead and I undo this, all right? So that meant this was 1/4, right? And we can hear. Here we cannot hear. No sound. So frequency, first harmonic, second harmonic, third harmonic. Now we're at the antinode again and we can hear. So we can hear the first, we can hear the third. We can't hear the second. All right. So what's going to happen at the fourth? We won't hear it, will we? Okay. All right, so the only conclusion that you can come to is that in a closed pipe, you're only getting sound at odd harmonics. Huh? What does that mean? What that means that, huh? That sentence? It means that if you've got your fundamental frequency, right? So something is 250 hertz. Okay? If you wanted to play the second harmonic, okay, you couldn't. You wouldn't hear it. Because as the wave exits the tube, the pipe, hang on. All right, as the wave exits the pipe, right at the end where the sound comes out,
It's closed.
yeah, you have a node there, so we can't hear anything. All right? That's what this is meaning, is that we can only hear when the sound is at its maximum amplitude, when the wave is moving at its maximum amplitude. There's no amplitude here, so there's no sound. So if we go on to the third one, for the third harmonic, well, that one hits at an antinode. And the antinode, that's our maximum amplitude, so it's going to be just fine. We can hear there. So for an open pipe, it's antinodes all the way on both sides, right? We can hear any harmonic on an antinode, on an open pipe, because it's always antinodes. But on a closed pipe, we can only hear every other one, because every second harmonic is a node on that pipe. Let's see if we can kind of put some stuff. Well, I think we're gonna call it good. That pretty much covers it. I've got 2 sample poems. I'm gonna go ahead. I'm gonna do them right now just to go ahead and get them into the recording. You guys can listen. Just don't talk much. Yes. Bell's gonna ring like in a second, right?
Yeah, I was upstairs.
Okay, fine. All right, so I'm going to go on to the next one and do the other problems. Okay, not that, because my slides are all out of order. There we go. Speed of sound waves in air is found to be 343 meters per second. We're going to determine the fundamental frequency, or the first harmonic, of an open-ended air column, which has a length of 67.5 centimeters. So that wasn't the button I wanted to hit. Here we go. So if this is 67.5, we know that what we're dealing with here is this. Okay. So we judged by our notes on the previous page that that's a half. So, whoa, excuse me. Wavelength is going to be equal to 2L. So that means our velocity is equal to frequency times 2L. Yeah, you guys can go. I told you what I'm doing. Y'all are doing fine. So what's that frequency? We know what our velocity is. We know what our length is. So velocity over 2L is going to give me the frequency. That's 343 divided by 2 times 0.675 meters, and that gives us that's going to give us 254 hertz. All right, next problem. Next problem is about, we've got a closed pipe this scenario, so that means that what we're looking at is for the first fundamental frequency is that it's going to do this. So in this case, our wavelength will be equal to 4L, because it's only a quarter of a wave there. So velocity is equal to frequency times wavelength. Frequency is equal to velocity over wavelength. Frequency is equal to velocity over 4L. 343 because it's sound. 4 times the length of the pipe, and that pipe is 1.525 meters. Okay, so it's 1.525. Therefore, we're looking at 56 hertz. That's the lowest frequency, all right, of a whooping crane. There we go.